Okay, all right, everybody. So let us begin. I'm just going to keep chipping away in the background. So as promised in class, what we're going to look at are IPCC data. So I'm going to just pull out. So if everybody could go just do a Google search on PCIC data portal. And I'm going to share my screen. I'm going to put that over there. Okay. So this is what I've got. Hopefully everybody's sort of similar. You can just click on data portal. And I think we've looked at this before. So we get various data sets, daily gridded meteorological data sets, BC station data, high resolution PRISM climatology. PRISM is that topoclimate model that we've referred to, parameter regression on independent slopes method. Hydrology stuff you don't care about for the moment. And then statistically downscaled climate scenarios. So click on this one. And then what we want is, sorry. Just make sure this is it. Okay, this isn't actually this. So this is another version of it. There are a lot of options. This is quite a good website. Sorry. Okay, right, this is the one. So the one you want is, I'm being so slow, come on. Oh, I see what you're doing. There's a little chipmunk or something. So you want the one that says PCEX, the Climate Explorer. So I'm just gonna go back in. Statistically downscale climate scenarios. And then this thing here, PCEX, PCEX Climate Explorer online tool. That's the one we want. So they have different ways of serving up these data. All right, so over here, this is what you get. This is the window we want. So what have we got? Well, we've got our little mapping window, so we can see the domain that we're working with. We've got a plot that it's whatever data we've asked for, it's showing us. We can do many different types of selections. So let's go back up to the top and we'll start digging into that. I think before, well, okay, we've got the models. So what are all these models? These are the models as we were looking at with the when we were talking about IPCC, you know, we said there are like 25 major models around the world that do these long-term climate projections. and the results of which contribute to the IPCC process. And this is it in terms of what we know. There is no other, source of data out there for for future scenarios. It resides with these models. So, and the interesting thing about this is a pretty straightforward way, actually, that PKIC has provided right here on campus to gain access to these data. I mean, anybody in the public can do it. Anyone can go to this site. And that's important because to deal with these data in their native format requires a lot of technical skill. I mean, the types of technical skills that you're coming up to speed in, actually. You're actually not that far off from what you've seen so far in class of being able to handle these files in a raw format. You just would need to understand a different type of file format called netcdf, a gridded binary self-describing data format, but not to worry about that. But they've kind of done that heavy lifting for us, and they've organized the data such that we don't have to download an entire planet's worth of data and all the variables and all that kind of stuff, which each file for one time step is like 500 meg. These are huge files. They've got this fantastic interactive access system, and that's what we're going to use. We're going to pull data for certain areas, for certain models, and then compare them to observed data. And that's what Adam's working on, a way to Environment Canada's data access system for weather data is a little strange. You have to write a program that loops through the date range that you want. You can't just say, I want 50 years of data, and it just gives you the file. You'd have to loop through every year in the data set. So it's actually a considerable barrier to people being able to download larger amounts of data. However, again, enough in Python, and with Adam's help here today, that you can overcome that. Excuse me one sec. Okay. All right. Today is end of fiscal year day, so there's a lot of traffic from the federal government on my email. Okay, so, all right, so sorry, let's go back up here again. So these are all the models, and you can look them up. I forget offhand what all of the different names. GFDL is Geophysical Fluid Dynamics Lab. Hadley is the Hadley Center. GFDL's in the States, Hadley Center's in Britain. Like Cicero, that's in Australia. Where did that one go? I saw that. Yeah. CNRM, that's in France. CAN ESM, that's a Canadian one. That sort of thing. So a variety of countries are involved in this. Okay, then we have something called emissions scenarios. And we looked at the sort of the older way of doing it, where they broke it down into A1, B1, and A2 and B2 kind of scenario families. And we saw that they had all of these different little subsets, and all of these potential futures would be given to these modeling groups, and then they would run them. These were, remember, they're based on social and economic models. And they kind of say, all right, well, if everybody suddenly puts up windmills, what will the trajectory be? Or if India says, forget it, we're just going to build coal-fired power plants, what would the trajectory be? All that kind of thing. So they think about all these things. But then over time, they realize that really you can represent these trajectories. You don't need to make quite so many trajectories, because in many cases, a number of them end up doing the same sort of thing. And they realize that, well, what we really need are scenarios that reflect what's the really worst case, however we happen to get there, and what's a really good case, again, however we happen to get there, and then what are some middle of the road cases. And so what they've ended up converging on are three cases. These are called RCPs, representative carbon pathways. And the number indicates the amount of additional radiative forcing that the atmosphere will experience as a result of the enhanced greenhouse loading that comes from whatever scenario is being realized. So in this case, 2.6 means we'll get an extra 2.6 watts per meter squared of energy in the entire global atmosphere system. 4.5, 4.5 watts per meter squared. 8.5, worst case scenario, 8.5 watts per meter squared of additional energy in the system. That's the bad scenario. And that's the scenario that we've been tracking on the whole time. So they've, ever since they started making these things, if you draw the lines, we're just bouncing right along with the 8.5 scenario. So, I mean, it's not even like, well, if this future comes to be, this is what we're realizing right now. It's the trajectory we're on. So it's just as an aside, it's going to take a huge amount to pull us off of that. Anyhow, so like the 2.6 is just, I don't know, it's kind of a fantasy. So it's nowhere near being realized. Okay, so then we have a bunch of variables that you can pick from. So I'm going to pick, let's pick a Canadian one, CanESM. We'll pick the bad scenario, excuse me. And then we've got variables. And look at the first variable. What were we just talking about? Cooling degree days. Just a second. I'm losing my voice. Sorry. Okay. So now we've got our variables. And so first one right off the top, cooling degree days. And remember, there's our threshold, 18 degrees. So anything below 18 degrees, in this case, means we're going to have to expend some energy to provide heat for the room. And there are all sorts of variables here. There's our freezing degree days. There's our growing degree days with a threshold of 5 degrees, just like we talked about. So again, they keep these in, even though they seem a little old-fashioned and simplistic. Well, they keep them in because they're basic indicators, and they do have a fair amount of utility. And there's also continuity with work that's come before, based on the degree day concept. Then we have a lot of other variables. I mean, this is a very rich website, a very rich interface. And again, you know, this is something that we mention as we've gone along. You know, if this isn't your last year, if you're thinking about honors or fourth year projects, stuff like this is a great place to get some pretty cool data. And this is, you know, this is state of the art. This is cutting edge. These are the newest versions of these IPCC models. So it's pretty interesting to work with, you know, because you can put it on your CV, right? Oh, I've worked with some IPCC data, and, you know, that'll raise some eyebrows. So, right. So even things like number of icing days, just basic precip, annual total precip in wet days. Precip is snow. You know, what's that proportion? Various, look, 95th percentile annual total precip. When daily precip exceeds 95th percentile. So basically, they've also got variables to try to account for the frequency of potential extreme events. That's what that's looking at. So all sorts of things. There's some of the things like we might be expecting. Daily maximum near surface. Remember, we just talked about that this morning. Not the surface radiative temperature, but the near surface air temperature, screen height air temperature is what it's often called. Daily min, near surface air temperature. Number of summer days. All sorts of very interesting variables, actually. All sorts of variables that are sort of ready tuned Like the models don't put these out. So what PKIC has done as an organization is to take the model output and do statistical downscaling work, but they've also created a whole bunch of variables that make a lot of sense in the urban planning or agricultural planning, like number of summer days, percent probability of extreme precip events, that make a lot of sense for a lot of different sectors planning needs, much more so than just using the raw data. The raw data are not suitable for any of that sort of thing. They need to go through this kind of process, and it's an extensive process. They've got little bits of info, little tiny bits actually. Right, so there's information about the runs. Oh, okay, so another point, right, we've got historical. Okay, so what does that mean? Well, the models aren't just run for the future, because you can create a model, give it some potential carbon dioxide outputs, methane outputs and stuff for the next 100 years and let it rip, and I mean, the models work, they'll generate weather and climate, right? But then the question is, well, how accurate is the model? And so what people will do with these models to basically validate them is to go back, say, to 1960, and then they'll give the models all sorts of data and they'll let the model run and they'll see, is it kind of reproducing the observed climate that the climate that we actually observed over that period? If it's unable to reproduce observed climate, then we're not going to have a whole lot of faith that it's going to produce a reasonable trajectory, a reasonable projection for us. Excuse me. So that's what a historical run is, and we have access to those, and that's what we're going to use to compare the actual weather station data to, because of course we don't have weather station data in the future by definition. So we're going to be using, like this here, it says can ESM historical RCP 8.5. Let's see, what else do we have here? Move that over here. So the actual interface, okay, so let's go to spot. Oops, sorry. Everybody's favorite city. Give it a moment. So good old Edmonton. So now let's pick, so what we'll end up doing is you'll be getting data from specific locations, like Edmonton Stony Plain or something like that. And you'll compare that to data that you get from this. So how do we get data from this? The one way that I use is I just click on this little icon. Come on. Draw a rectangle. Oh yeah, no, sorry, I guess that was it. So I just use the little draw a rectangle icon. Oh, there we go. There's Edmonton. It's hard to see, but I've got a little rectangle. Oh, another point, sorry. Okay, here where we've got, so this is Cypress Hills down here in southern Saskatchewan and south eastern Alberta. And you can see the pixely nature of the data. So what that's telling you is the data are gridded on a 10-degree or a 10-kilometer grid. Actually, this is a good opportunity to show you something. Yeah, actually, this is a super opportunity to show you something. I thought about this. Okay, so you remember we talked a little while back about model representation. So this is a numerical model. This is like pure physics and pure math, all the equations jammed into this modeling system. We've forced a computer to do calculus for us, and it outputs things on a grid. Now the native resolution, the original resolution of an IPCC model is not 10 kilometers. It's much bigger than this. So the grid boxes are even larger. Part of the downscaling process is to produce data at this finer resolution. But the important thing is that we often see, representations of model output, but then you've got this beautiful little coastline. You don't see the pixely stuff, you see contour lines, and then you'll see the coast. And you kind of get this impression that the model sees the coast as well. Okay, well, the pixels are what the model sees. So you see, no Vancouver Island. Look, it's actually connected there to the mainland, like at just north of Nanaimo. And north of Campbell River, forget it. You know, there's no ocean in between there. There is no Vancouver Island in the model. And this is kind of like some bizarre small inland marine lake or something. And the coastline, you know, it looks nothing like that. The San Juan Islands there, no, they don't exist as far as the model's concerned. And then if we were, it would actually be cool if we could plot topography. So topography is similarly poorly represented. You think of a narrow valley that maybe is only 5 kilometers across. You know, like think of the valleys if you've driven in the interior up the, well, as you go up the Fraser River and Thompson River, you know, some of those valleys are pretty narrow. And if you've got 10-kilometer pixels, you might hardly be representing that valley at all. So, and you can kind of see that here. You know, you see some of the valleys are just fairly weakly represented by these pixels. So it's an important thing to bear in mind, and it's the reason that an exercise like this, where you take actual observed data and compare it to the model data, is a good exercise to kind of drive this point home. All sources of data are useful and not useful. You know, all models, all sources of data have their utility, but it's very important that you recognize where the utility exists. So what you can use data, a given data set or a given model for, and what you can't do with it, you know, and what you can expect out of it in terms of, say, resolution. You know, this came up with the sea ice lab. You know, a number of people felt that the variability, you know, there's a lot of annual variability in the sea ice data. And a number of people were expressing the idea that they felt that, you know, there was a problem with the data. And that, well, you know, if we could get better data, we would have a better fit or something like that. And the actual fact is, that is the highest quality data possible. That's the best data you'll ever get. That's a precise representation of the area of Arctic sea ice derived from satellites on a daily basis. What the data are reflecting is the inherent variability in that natural system. You know, it's just a highly variable system. And so, you know, understanding where the data have come from and what you can do with it, what it's going to give you statistically, you know, these are all kind of things that you have to get used to. And so it's the same thing with a model like this. You know, these aren't magic, and they've definitely got limitations in terms of what they can resolve. You know, and so that feeds directly into what can you use them for if you're doing something like engaging, you know, the city of Vancouver, when you're talking with them about potential impacts of climate change, you know, for their urban planning issues, you know. All right. So let's go back to our friend, Edmonton. My cousins live. Some of my cousins. Okay, so now if we go, so we can do various things here. So we've got annual cycle, long-term average, model context. What am I missing here? Okay, so that's the one I was thinking of. Model context. So what this one is doing is, instead of you having to go pull out each model separately, it's showing you for this little box. I mean, this is actually a very powerful interface. There's a lot of work that's being done, what's called server-side processing. You at looking at it, that's client-side, server-side. So there's a lot of things nowadays to do a lot of server-side processing. They do all the work and then serve up just the data or the image that you are wanting. What the model context shows is the model that you've selected is in orange. All the other models in that list are in gray. So, I mean, you can see, like, again, this is for cooling degree days below 18. I mean, we just kind of ended up picking that one. This is historical here. It's a little tricky to read. Like, there's 1986. So that's probably, 2006, and that's 1966 or something. Historically, most of the models are pretty well constrained. But as we proceed into the future, like to 2085, so what is that? 60 years into the future, we can see the spread in the models. And we can see that a number of models track a little higher, kind of another group we're tracking here. We've got outliers. Canadian model is looking almost like an outlier, and we have some other outlier down here. So, this is always an interesting exercise as well. And what people find out over time is that, you might say, well, I'm going to do this work for the city of Edmonton. I'm going to pick one model. Well, which model are you going to pick? There's quite a spread there. So you say, all right, well, I'm going to pick a bunch of models and average them, or I'll take all of the models and average them. That's probably unnecessary as well, because that's a whole lot of work. So what we end up with are, oftentimes people will do studies. Like, I can remember one in the Alaska Arctic context where there's a big study performed, and they identified the 5 models that seem to work best in the Arctic context. And then that's what people will use. So, I mean, we're not going to do all that, but that's the response to a fair amount of variability amongst the models. But you still having to, you still have to give the client, in this case, Edmonton, something to work with. You can't just say, oh, there are too many models and they're too variable, we can't do it. That's also not the answer. So this is also, just, it's an interesting point to kind of take home, that we do kind of get a lot of spread. Change from baseline. I think I've clicked on that. Right, so this is sort of telling you when in the year you're getting changes occurring. What snapshot does. Oh, okay. It just gives a snapshot in 2055. So what we can then do as well is, I'm going to pick, let's not do cooling degree days because we have to do calculations. We're just going to do, here we go. So daily minimums, let's pick that. There's our annual. Let's see, we can pick different time periods as well. Annual for, these are our observed periods, so our historical. And then we can start going into the future with these. I mean, you can play with that. It doesn't, I mean, just looking at one time, they all show it's warmer in the summer and cooler in the winter, so that's not helpful, but it's the comparisons are what we need. We're not going to be using the future ones, of course, but we'll be interested in these past ones. And we can go down here. Here you can pick specific months, specific seasons, or annual. So I think just for simplicity, because the winter is always an annoying season to calculate because you're going over a year break. So let's not worry about that one. We'll end up picking something like a cold month like January, February, and then a warm month, you know, like August or something like that. Runs off and gets the data. So there are our August values for CAN ESM, historical run, representative carbon pathway, or concentrate, not carbon, representative concentration pathway, sorry, RCP 8.5, averaged minimum air temperature. And then what you can do is just click CSV or Excel, I mean, whichever one you want, and you can just grab it. So there it is down there. It's going to open it in Excel. So there, and now it's, you know, you can grab the data and start doing something with it. So yeah, in a sense, that's sort of it for the web page. You know, it bears a little bit of playing with, getting used to it. Like I say, it's very powerful and it has a lot of options. So yeah, so do spend some time with it. And so what we'll be doing is picking several locations, such as 2 prairie locations, 2 West Coast locations, that sort of thing. And we'll be looking at how the observed data that you get from the weather stations, you'll take those data, reduce it to a form that's very similar to the models. In other words, these multi-decadal averages, you know, for a month, and then compare them. So for say for Edmonton, for August, for 1961 to 1990, you'll have the observed data, but then you might have, say, 5 models, and there'll be a certain spread around that. And you repeat this for various locations. And in the end, you'll want to just comment on what you think reasons for the spread might be. You know, just thinking of things like we just talked about with the grid spacing and the ability of a grid pixel to capture the detail and the variability that's expressed in the landscape. You know, and of course, I mean, the punchline is going to be that, well, prairies are probably going to be a little easier because they tend to, you know, you go to southern Manitoba and it's pretty flat if you've driven through there. Whereas around here, a lot of topography, you know, there's a lot of opportunity to miss the details from a weather and climate perspective. So we would be expecting, you know, kind of our hypothesis, instead of just kind of throwing data onto a plot and wondering what might happen, you know, we go into it with a certain expectation. And the expectation would be that the model results for the prairies are going to be a little tighter than they are for the West Coast. And so you can, yeah, so you'll be able to basically dig around and have a look at that. Any questions on the gridded data or the website or anything like that?
I think just one. When we're selecting our data, does it really matter that much what area we choose as long as it's within one grid cell?
Oh, I see. So in other words, like, so if I throw that out. Oh, click on a feature to remove. Right, so you're asking specifically like how big, you know, does our little thing have to be? Yes, no, it integrates whatever it's crossing. So if it connects to 2 grid points, it's going to grab them both. But like for a place like Edmonton, there's not a whole lot of variation. So in fact, it's difficult actually to see, like on this plot, where one grid point starts and another one ends. It's not going to matter that much. On the West Coast, yeah, you'll have to pay a little bit more attention, but then the variability should be a little more obvious. And you know, you could even try something like putting in a different variable to make it a little more apparent. And I don't actually have a good suggestion. If we get more precip. Yeah, no. So yeah, there's probably not a particularly good suggestion for Edmonton. So I think grabbing, you know, in the vicinity, I mean, the thing that you'd probably want to do would be to figure out where the station is located and then try to make the grid point in the vicinity of the station.
Okay, thank you.
Yeah, this is a really cool site, actually. There's a lot here. I haven't looked at it in too much detail before. I thought about it for this class. Annual, which is averages. Does everybody have co-host?
Yeah, I think so.
You gave it to them?
Yeah.
So,
Did you show them the Environment Canada site? I mean, I know we've been there.
okay, yeah, no, I didn't. Thank you. All right, yes. So where are we getting? We haven't been there, have we? I keep thinking that we'd seen it, but I don't think we've seen the water site, but not
Maybe not. I would
the
have
weather and climate site.
expected that they had.
So yeah, no, like I don't think we've actually looked at this. So historical. Historical data, climate. Environment Climate Change Canada. An annoyingly long name for a federal group. Actually, Crown Indigenous Affairs and Northern Development. That's actually worse. So, okay, so this presents a fairly straightforward page. So we start off with pick your city or your search term. Search. And this is what I was saying. There are a lot of Victorias in the country. 2 pages of Victorias. So, and I think I've made this comment before when we looked at, remember we did the built the empirical data model for Victoria, and we ended up pulling out a Victoria PEI and a Victoria Newfoundland. So just always be sure. You know, you could find a city of Victoria and then realize it's like in Manitoba. So there's our PEI, there's our Newfoundland. Well, there's one in Ontario too. So there's one in Toronto. All right, so the Victoria is all over the place. So you have to be a little careful and be sure to get what you're getting, because unless you've got a pretty fine feel of what the data are going to look like, that's a mistake that will easily slip past you. So okay, so what we've got in terms of how they serve the data up, let's pick one that's, excuse me. All right, so Victoria International Airport, we've got this little marker, hourly, daily, monthly. Okay. Not all stations have all options. So some don't have any hourly data, just dailies and monthlies. I think usually if they've got hourly, they've got the other two, although I think I've seen it where they don't have monthlies, but at any rate, so you can select the frequency. Whatever years are available in the data set are listed here. So Victoria International Airport, the first one, goes from 1953 to 2013. They must have moved the station or something because the record is broken, and then it's continuous, but we actually have to get 2 separate files and stick them together, and then be very careful of the point where we're sticking them together at, because that could easily be a discontinuity, you know, where you get wind going along and then suddenly the wind's 2 knots stronger on average. You know, there's nothing to do with climate. That has everything to do with this metadata, with locational issues. Oh, thank you. So hourly, daily, monthly, the year, and then you pick the, well, if it's hourly, you pick the month. If it's daily, you still pick the month, but now you don't have the option of a day. And if it's monthly, you just pick the year. So, for example, if we pick dailies and July 2013, let's pick not the very end of it because it's probably incomplete. Let's pick 2010. Oh, actually, I know what we'll pick. 1996. Just one sec. December 26, 1996. That's what it was. So December of 1996. Go. Okay, and so this is what it gives you. The daily data report for December 96, daily values for these various parameters. Again, heating and cooling degree days. So yeah, it's extremely common. That's right, the Great Blizzard of 1996. No, exactly, yeah. So I just was curious to see what, yeah, so look at the snow. See the snowfall values here. Goes from 0, 0, 0, 0, 0, 3, 14, and then 19, 19, 15, 18, all the way up to 67 centimeters of snow on the ground at the airport. And I know it was more. I mean, that's at the airport, and you go anywhere in the uplands and you always get like twice as much. So a lot of snow. So you say, okay, well, that's great. I want these data. And so you can go over to here and download the data. Again, CSV, Excel format, and then just a TXT format. Download the data. So that's great, Ed, but it just gives you December of 1996. And you say, well, okay, that's great, but I want 5 years before and 5 years after. No place to select a date. So you say, oh, if you want more data, you got to go here. Okay, and so then you get this stuff.
Which is where I've been for the last.
Yeah, and so this brings
2
us
hours.
to welcome to Adam's world sort of thing. So, so what we've got here is, bizarrely enough, a Google Docs drive, which is very bizarre for the federal government because they're pretty hyper about this with good reason. They don't want to be hacked. And so what we've got here is a station inventory, and then some other bits of information. And then we've got a README file, which basically tells you how to go about getting more data. And what it's going to tell you is basically something like this. Fine. Oh, it's going to open it right in here.
You just double click on it, yeah.
Oh,
I just don't understand why.
authorized text editor. Oh, for God's sakes.
Why is this?
Just open it. Oh my God. Preview. Maybe that's what. Okay. Can you guys see the text thing that's open?
Yep.
Yep. Okay. Thanks. All right. So what we've got, actually, I have another. I can see. I can see what I'm putting up. All right. So what we've got now, this is where we get fairly strange, although a little less strange for you because you've seen coding now. But this would stop most people pretty dead. This is text. This is what you would run at a Unix prompt. So at a command line for a Unix system. So it's a little what's called a shell script. And so here's a little of, it starts a for loop. So for year in, I mean, and you know, an interesting thing about all this is once you start learning one language, you start to immediately recognize the structures in other languages. You know, the syntax is a little different, but you know what a loop is now. And you can recognize a for loop in any language. It's basically the same. It's for some variable in some range, and that variable will take the value as it iterates over that range. In this case, our range is, and this is a Unix thing, which you don't have to worry about, but it generates a sequence of numbers from 1998 to 2008. So year is going to take a value successively starting in 98 and going to 2008. That ends the line, a semicolon. Do what? Start another loop for month in 1 to 12. Okay, so that's called a nested loop, a loop within a loop. So now it will run through month equals 1 to 12 and then tick over the year. Month 1 to 12, tick over the year. So it's the inner loop always has to complete before the outer loop gets its next tick. Do what? Well, run a function called wget. And that's just, it's a Unix command line thing that will go to a website. I mean, we're used to going to a website, we see a file, we click on it and it will download. Well, wget does that at the command line. Why is that important? Because as we're seeing with this Environment Canada data set, you have no option. If you want to get 50 years of hourly data, like we saw 1953 to 2013 from the airport, there is no way on their website to say, I want 53 to 2013, download everything. You can't do it. You have to run these little programs. Like I say, it's quite an impediment to people getting the data. So it becomes very much a non-casual thing because it requires a lot of technical skill to handle this or to do it the way Adam's going to do it, which is within Python, which is actually a lot cooler.
If it ever works.
If it works, yeah. Blah, blah, blah. So those are that's just an argument. But then, yeah, so you give it the website. There's the whole website, all this stuff. And so in here, embedded in here, so there's the station identifier. So each station has an identifier. I think that's Yellowknife, actually, strangely enough. But then you tell it what year you want.
It is Yellowknife.
Dollar squiggly bracket, close squiggly bracket, tells Unix that the year is a variable that it's taking from up here. Same thing with the month. The day doesn't matter if you're getting a month's worth of data. It doesn't matter which day. So that's why you set it to whatever. Download data, done. So that's for each of the for loops. So all it's doing is looping through these 10 years or 11 years, because it's inclusive, every month in every one of these years, and it's downloading a separate CSV file for every month. So, so you end up with a big pile of files. And so that's, you also see the power of something like glob, which is designed to read in, to do sort of a bulk read of all those things. So that is the Environment Canada data. Now, in terms of, so let's go back to the, sorry, I'm just going to check out hourly ones. Hourly 01 is, it used to be at Environment Canada that they had all these data stored in these formats like hourly 01, daily 04, and stuff like that. And you could get an account on their mainframe. This was like 1992. And they had little Fortran programs, which is an older programming language. I mean, we don't teach it now, but a lot of people use it. Like for these climate models, they're all written in Fortran because they're all so old. And yeah, you would write these little Fortran programs that would access the database and do dumps, and then you would upload it to your 1993 version of a laptop. But they still have the same format. So what I was going to do is okay, I'm going to switch, stop the share, start the share again. Share. Okay. If you download the station inventory, yes, station inventory, this is what you get. So if we just open it out a little bit. So we've got the name, the province, climate ID. That is a 7-character identifier that Environment Canada, well, I mean, I don't know when they started to use it. It's always been around since I've engaged with them, but like, let's see, 240 is the Arctic, 1200 I think is Eureka, if I remember correctly. Yeah, so that's Eureka up in the high central Arctic on Ellesmere Island. But, oh, the station inventory file, sorry, if we go, I'll show you in a sec. Yeah, we'll come back to that in a sec. So even though this is Environment Canada's identifier, for whatever reason, they don't use it in the line of the file. They have another identifier. So they have a climate ID and a station ID, and I've never been 100% sure what the difference is. So like if we look up here,
I got it.
1706.
Jeez Louise.
Right, so there's 1706, so that's Yellowknife. So the important point about this file is for performing the access that Adam's coding up, or if you know Linux, you can use the other format, I don't mind. You have to use this, you have to use the station ID in that string. In that, basically it's a URL, a universal resource locator string, you know, HTTPS / et cetera, et cetera, et cetera. That's a URL, and the station ID has to be this one, not the climate, not the World Met Organization, not the Transport Canada ID. So just the station ID. And then, you know, that's kind of about it in a sense. This tells you where the file, where the station is, Latin long. Oh, that must be Eastings and Northings, right? What is that? Anyhow, that's a little weird. I don't know what that is actually. Oh no, it's sort of latitude and longitude. It's just, decimal degrees. I'm not sure what the difference is. Oh, no, I know what oh, Adam, this is weird.
What's that?
It's degrees, minutes, seconds, but they've smacked everything together. So like 48.87 is 48 degrees, 52 minutes, right? 0.87, but they've just kind of jammed it all together. Wow.
Weird.
I've never seen that actually. So you guys see, it's like, you never know what you get. Every single data site is got some strange and weird thing. No two are ever the same, which is kind of unfortunate, but let's keep on creative. We have station elevation, so the very basic metadata, and then info, just so you can do a quick search on what is the date range. And so I had started to run a filtering process so that you weren't attempting to choose from quite so many stations. Yeah, so there's somebody with 100 years of data. Who the heck is that? Shemanus. Oh,
really?
wow. Okay. Who knew? So anyhow,
Almost at the moment of truth to see if
so
this
what I'm
runs.
going to do is, I mean, Adam will take over here in a minute, and then I'm going to prep a file of just limited options that you guys can work with, just so you're not going in too many different directions. Okay, so stop share. And I think you guys have co-helped each other, which is good. You learn much more than just listening to one of us talk at you.
Look at that, just in the nick of time, got it to work. Huh. Okay, great. So over to me, I guess.
Okay, well, just one sec. So I'll show them where to get that file. I think the important point is you can't gain access to that directory without first doing a data request. So like, I'll just go right to the back here. So, okay, so we pick, our station, let's pick someone new, Calgary. You get your options. There's the Glenmore Dam, which we were talking about. Dailies.
Are you showing them how to find the station ID? Because I could use that.
Yes, so yeah, we'll be getting there. So
I'm not
so
sure
we
where to go.
start with just some data request, doesn't matter what. Sorry, say go. And it gives you the data, but then it gives you this thing right here, download data. And so when you click on get more data, there it is right there. Station inventory is the first option as the CSV file. Anyhow, I already downloaded it and then stuck it into the Excel format.
Stormy, you're going to get to pick. Everybody's going to get to pick. The idea is, though, you've got to pick one that's got at least 30 years worth of data, which is why David was talking about that. Get more data to try to find ones that have enough data for our purposes.
Yeah.
How do I find the station number? I have to go through get more data and find it.
Yeah, you have to open up this station inventory. Oh, do you mean if you've
For the get request? How do I know the ID?
right? Okay, so okay, let's go back one. That's actually probably the more relevant question. So
because I could just search the Excel doc or the Google Docs doc. Oh, it's the climate ID, right?
okay, yes, yeah.
Yeah, I think it's the climate ID. Okay, so that's fine. So it's on the. I
And
know
I'm
where to
just
get
going to
that.
double
I'm
check
just gonna
with
test
Yellowknife here.
mine here. Delete all my files. Yeah, I just got. Oh, that's so great. All right, everybody's gonna have to pay attention today. We are working with directories again. I am pretty happy with this little script, actually. Took a while. Okay, great. So David, I know you wanted to run off. Was there anything else before we?
Yeah, I just want to verify this climate ID thing, because this is actually, I remember this was a problem in the past.
I've just done it.
Sorry?
That's not right. Oh, no. Oh, maybe you're right. Maybe it's not climate ID.
Yeah, no, station ID, right. Climate ID is that their main database thing. Yeah, so they don't make it easy. So
No, they don't
Yellowknife
seem
is
to do.
actually for 5 different potential numbers. Yellowknife Hydro.
Is it column D?
It's column D, correct, in that CSV file.
Gotcha. Okay, that makes more sense.
So Hydro ought to be 1707.
Column D. 2941. Or I say that this works. Let's.
No, yeah, you see, it doesn't, which is
Column D doesn't work?
no column D. And this oh yeah, that's right. So this is where this gets pretty bizarre. So column D, like here, I'm gonna open up, I'll share again.
Mm-hmm.
Like I say, they don't make it easy. I don't know what the deal is. All right, so here we've pulled up Yellowknife Hydro. I know that the station identifier for our purposes is 1707. That's the station ID. But for whatever really weird reason, it is not up here. The climate ID will not work for searching on these data. Up here, if you go, there's the search, or there's the URL. If you look here, station ID equals 1707, and that's where we had to pull it out. Yeah, and we've been down this road now that I remember. So
Yeah.
And that's where we had to capture it from.
The way that I did it was I took that Excel doc that was on the Google Docs, searched for the climate ID, and then pulled the station ID from there.
Yes, yeah, that's right. I mean, the thing
It's
to
easier.
do,
It's just in the web address.
that's right. The thing to do is go back.
Okay, we are running low on time. You should get these guys.
Yeah, underway. Yeah. Okay, all right. So I'll surrender control. Okay.
Great. All right, everyone paying attention, because you're going to get the code in the chat. So first cell that we do is what? Always. Somebody speak out. Oh, I need to be able to share, David. You took it away from me.
Oops.
Import our libraries. Great. Which one do we always use? I still can't share, David.
No, yeah, I'm on the wrong.
Pandas, that's right. All right, get pandas in there. We're going to use two new ones.
There you go.
Great, thanks. Use two new ones this week that you haven't seen before, and they may need additional installation. So this is going to push your memories back. Which, I'm going to share that one. Push your memories back to the first week when we started installing libraries. Which screen am I sharing? Can everybody see my code?
We can see it.
Okay, so you can see import pandas, etc. Yeah, okay, good. Zoom is in a different place right now. All right, so yeah, everybody, you want to bring in your pandas library, you got a new notebook set up, name it accordingly. And we're going to add two new ones this week. You want to import requests, and then from iter tools import product. Try putting those in there, try executing that cell. The likelihood is you will have requests that works because it's just part of our Python package. It's not a third party, or not third party, I shouldn't say that. It's not an additional one. But the iter tools is. So that one we will have to install. All right, both work for Nigel. That's great. Anybody not have iter tools load for them? Would be a better one. Great, even better. It makes me happy. Good. All right, good. Well, let's assume it works for everybody, unless otherwise noted.
It does not. I'm not getting it, so I'm gonna have to do it.
Have you got it verbatim here?
Yep.
Because if other people are getting it, I'd be surprised that you don't have it, since we all loaded it together. So just double check if it really isn't there. No, it should be there. I don't know if we want to go down the path of it not actually being there. Does it say that iter tools is not, like the error message is iter tools does not exist?
Got it. My code was bad.
Okay, great. All right, so moving on. All right, so you've got that loads in there. Great, wonderful. This second cell here, I'm going to send over the chat because you don't need to write that all down yourself. let's make a note in here once you've got it there. Replace the year with your year of interest. Okay, that's important. Otherwise, you are not getting your data. All right, so let's just go over what this is doing just quickly before we jump into getting the station data, which is where we need to get to this week. I've got a year range and a month range, and they are doing basically what they're saying they're doing. The first one is creating a year range. So since everybody knows how to test our code, then it's perfectly easy for them to hit execute on our libraries, for everybody, sorry, to execute on our libraries, execute on this one that I've sent copy and paste, and then we can take a look. If you take your variable, put it into an empty cell, take a look, it shows you what it's given us, right? So month range is 1 through 12 integers, right? And then year range here, same kind of thing. I've said 2008, but oh, and the number and set the number of years as the range. Oops. Okay, so here you can see that my variable year range has got 2008 and 2009. The reason it has only 2008 and 2009, as I've said, 2008 for the range 2. If I change this 2 to a 10, now I'm going to get 2008 through 2017. Okay, you don't need to modify month. There are only 12 months in the year, so don't have to worry about that. But your station that you'll be pulling will have a certain number of years in it. And so actually, you know what we'll do here? I'm just going to confuse everybody. But if we change this to a negative, then we can always grab the most recent year. It doesn't really matter. So anyway, the year starting plus the number of years into the future you want to have. Here I've got 2008, range of 10, gets me to 2017. Okay. This line here, date range equals 2 close brackets. That is just setting an empty list. Again, we've talked about data types before. We've dealt with Panda data frames, columns, and rows. We touched briefly on series last week, but that's another data type. And I think in the past we've glazed over or glossed over lists. So date range equals close brackets, just empty brackets, just creates an empty list. Okay, so if I were to do this and then go date range like that, it just shows you 2 brackets, an empty list, right? Whereas when we looked at year range, it was a populated list inside our square brackets. Okay, all that's doing is empty list. It's creating the variable, in this case, the object. And then we have a little loop here. I'm not going to go into too many details, but this loop pairs up our months and years. So if we run this cell and then we take a look at our date range, you can see now that it's got 2008 first month, 2008 second month, third month, fourth month, fifth month, and so on for our 10 years worth of data. So this has created ourselves a paired list for our date range of interest every month. Okay. Don't need to go into too many details here, but product is coming up from here from our iter tools, import product. Product is the function, product, year range, month range. We are combining our year range and we're combining it with our month range. And for each of those pairs, we are putting them together into my list that we've created. All right, so that's what's going on there. You don't need to mess with it too much. You don't need to do too much with it, other than knowing that you set your date range and it will give you a output list of the range you need. Okay, the next one here, I'm also going to copy and paste into the chat there. And so you can copy and paste that directly into your Jupyter notebook. Now, do not run this yet, okay? Please do not run this yet. I want you to make a note at the top here, since we already just did that copy paste, and I want to go enter your station ID of interest in the string below, where it says station ID colon station ID goes here. Okay, make your note so you know that in this segment of code here, you need to change segment ID right here. So segment ID, station ID, and you put the number in there. All right, so this station ID, this is coming from when you're looking up your station. David just pointed this out. It's the last thing he did before he left. In your URL string, it says station ID equals 2941. So this one in Saskatchewan is 2941. I took the 2941 and placed it right there as my station ID. Okay, it's important you make a good note here so you know what station you are pulling. All right, okay, do not run this yet, as I said. This next step is really important. I'm gonna pause for half a second here, and I want everybody to catch up on any notes, make sure they're caught up. No more panics. Basically, it should have been 2 copy pastes and 2 notes. So I don't think I'm moving too fast. All right, the only thing there that we're changing is the station ID. We do not need to change anything else. The first cell here, the only things we're changing are the year and the number of years. Is it the station IDs we can find in the station inventory Excel file? It's what I just showed you, Madeline. So right here, when you're going through the Environment Canada and you look up and you find your station that you want to pick, and yes, if you're going to go through the Excel inventory and you find your station by using this lookup to figure out the number of year range, then the station ID column here, correct. You can pull it from the station ID column. Else, you can pull it from looking up your station by name or by climate ID in your Environment Canada historical data lookup, and you can find the station number up here. So yes, thank you, Maddie. There's 2 or more places that you can find your station ID. Great, good question. Okay, station ID. So everybody take a kind of so we only change the number. Yes, enter your station ID of interest in the string below where it says station ID. Station ID goes here. Nothing else needs to change. All right. Now, that being said, do not run this cell yet. It will not work. What I need everybody to do, or this will not work. Okay, everybody needs to do this. You need to go sorry, let me just clear this out so that I do it the same as you are. Hold on, bear with me. Okay, so in the third one we did there, there's a line that says file name. After that, there's a name called lab_5_data files. Copy that verbatim. Every letter has to match. So just do copy on that lab file data files. Then navigate back to your Jupyter kind of home page, right? So this is the file directory where your notebook lives. All right, so whatever it is on your computer, you are looking at this page where you see your Jupyter notebook that you are currently working in. So you can see mine here, Lab 5 Week 1. That's where I was, Lab 5 Week 1. I see that file right here in this list. Once you're here, once you see that notebook is here, what you're going to do is over on the left-hand side, there's a drop-down that says New. This is the same place you've been going to start a new notebook with Python 3. If you go down a couple of lines, it's going to say Folder. Okay, we want to click on New Folder. It will create a new folder in your directory on your page here called Untitled Folder. Click on the little box beside it. Once you've got that little check mark there, if you go up to the top on the left-hand side, one will say Rename. Pop up with our familiar rename, because we do the same pop-up appears when we rename our notebooks. Paste that file name in there. Okay, no spaces, no extras, no uppercase, no lowercase, just lab_5_data files. Don't forget the S. Once you've got that in there, hit rename, and you're good to go. Once you've done that, you will be able to execute this third cell. Now, before you do that, you're going to have to pay attention to what it's doing. So let's, as an exercise, do this now. If you execute, and for continuity's sake, I'm just going to restart my kernel just from what I've been doing. All right, so from the very start, load my libraries, execute. Second, I'm going to change my range just for this little exercise. So I would suggest you do the same. Just pick a year, any year. Just set the range to 2 for our little test. Then execute that cell. Once you've done that, we know we've got our lab 5 data files directory. You can leave the station as is for now for our test and execute this file. You'll see the little asterisk pop up. This is going to be the longest executing bit of script we have done to date. All right, there you go. Mine's finished. Yours may take a little longer or faster, but the little asterisk has gone away and now replaced with a 3. Once that has completed executing, go back to your Jupyter homepage to that lab 5 data files that we created. Okay, so we've executed cell 1, 2, 3. We've come back to our homepage. Now let's check out what's inside this new folder we created. Magically, there are, bang, a ton of files in here. There is a CSV file for each month, for each year that we set up in that data range. Okay, to give it a little test, you can click on one of those. It'll open a new tab in your browser, and you'll see a wonderful looking CSV file. Okay, yours should look like this. You should be able to see, if you haven't changed my station number, you should be able to see that it's Langenberg, being the station that we selected. You can see at the top, there's some headers, total snow, total rain. This is exactly the same as this grid from the website. It's the same data. All we've done is we've used a batch process of looped GET requests to pull every month of interest to us. All right, so you can close that CSV tab, and then if you are back on that Jupyter page with in our lab 5 data files, what I'm going to need everybody to do, again, I hope people are making notes. This is being recorded, so we should be okay here, and I hope not to move too fast. If you have missed any of these steps, please speak up in a moment. If you're in here looking at all your CSV files, okay? At the top left, there's a little checkbox that if you check that checkbox, it selects every file in this folder, okay? Why this is going to be important is because when we're testing, we just ran a little test, all right? So these are our final data files. It's just a little test. It's going to be useful to be able to delete this entire folder, the contents of the entire folder. We do not want to delete the folder ever for the length of this lab, but we may have a use to delete every file within the folder, okay? This is, I don't know, maybe you change your station, maybe you change the number of years, maybe something didn't quite work. You're gonna need to know how to delete all of these without having to go and check every single one little box. So as an exercise, I can select them all, delete button. Do I want to delete all 24? Yes. And now my folder's empty again. Shoot, I wanted those CSV files. Well, look, super nice. We have a code to do that. And it only takes a few seconds to load. Once my asterisk disappears, I'll have all 24 files back in there. Bang, they're back. All right, so you can start seeing the power of that. So whether you deleted them or not, up to you. Make sure you've got them loaded back in for our next step in our test. Import libraries, set our date range, get our station ID and load our station data for our date range. The next thing we do, like we've done on every lab, I think, to date, is we bring our CSV file in, okay? Now, I always just start with read CSV and the file name, okay? Just like we have done before. And I'm just going to take one of my file names. I'm gonna add something to this for everybody, but for now, you know that it's in this folder we created, lab 5 data files. Make sure you separate that with a /. And we know we've named them, we just looked at them, 2008_1. We know we've got one there, and it's a CSV file. So if I just test by read CSV, no other parameters, and take a look, bang, looks pretty good, right? This is something we can work with. Again, this nice little lookup, right? It is identical to this. It is the same data. We've just gone and got everything we wanted all at once. And now we have a data frame in Python for our station climate data for any year and month we desire. All right, that was a lot of information really quickly. But I want to get one more step in, and that is, this is going to be pretty laborious if we want to take, 30 years worth of data per month. How are we going to read all of those CSV files in? And this is a question out to everybody. David saying station IDs are in the same station. Oh, yes. Madeline, Glob, yes, thank you. Perfect. Which lab did we use that in? Was that 2 or 3? When did we? It's always nice to copy paste. So if we go back, doesn't look like it was 3, so it was probably 2. Anybody remember? Was it 1? Did we start?
It was 3.
Was it 3?
Yeah.
Okay.
Yeah.
Oh, there it is. Yeah. Okay, great. So let's just take a copy from our lab 3 notebook, and let's throw that in here and see if we can leverage that. Now, we did need to load another library, didn't we? We've got Glob in here. So if I bring glob over, so here we go. We've got import glob. We can add that to our libraries load at the top when we're ready. We've got our pandas concat. We've got a pandas read CSV. We've got an F here for our file name. So now we're a little more experienced. Why don't we be a little more explicit? So if we call that file name, where's that F coming from? Down here. So you don't have to rename it. You can copy paste it. Know what works. File name. Okay, we've got some other parameters here. We've just tested it. We're not interested, right? We're not interested in any other parameters right now. So let's just take those other parameters out. Okay, just for this first step. And then we know our folder name. Okay, put our folder name in there, lab5 data files /* for all of the CSV files. Okay. And then we've got an ignore index. All right, well, let's give that a test. See what it does. Oops, it's not what I meant to do. Boom, that's fast. Wow, look at that. We've got 8,700 rows in 31 columns. That was surprisingly fast. Wow, cool. Okay, so that's it. We're going to leave the last 15 minutes for questions, tests, testing, validation, etc. But what we're going to do, what the goal is that you've got these 4 cells set up into your notebook. You've got your lab5 data files set up. And now with the review that David did at the beginning of class, you can go out there, hunt down a couple of stations. Now, if David wants you to pull more than one station, no, that's fine. Okay, so go onto the internet, go onto the websites, find your station IDs, go hunt them down. Take one of those station IDs, run this for your station, right? Make sure you clear out your folder for your date range on the test we just did. Put in the date range of interest. It's here, Stormy. There you go. So find your station, find your date range of interest, right? Which year it starts in, the number of years. Keep these numbers smaller if you're testing. Once you've got the right station, you've got your CSV files loaded, then expand it out to your full range, okay? And it will bring your glob, will bring in every CSV in this folder. Okay. Luckily for you, you do have these great couple of columns in here. Your station name, and although station ID isn't on here, climate ID is. So if you end up bringing multiple stations into your lab5 data files and globbing them all together, you can do it that way. But I tell you what, why don't we add something here to make it a little more explicit, right? Because our little asterisk here works pretty well. But what if we were to specify our station ID 2941 in front of it? It's going to look for every CSV file in that folder that starts with 2941. Okay, but right now they don't start with 2941. So to achieve that, we are going to parse things out a little bit here, okay? Try to follow. I will copy and paste this, okay? Station ID, station ID equals our station number 2941. Now I've set a variable that equals that station number, okay? So what I can do is I can replace the string in my parameter list, which we didn't discuss, with my variable, okay? just like I did with year, if you were paying attention to these values. Also, that doesn't put it in our file name, but we're also building the file name here, which gives us some power. So if we put our station ID variable in here, also making sure that you've got your add symbols in here correctly, you're also going to want to separate it for continuity's sake with an underscore. And so nobody panics. I'm going to pass you this. Okay, so if that was just too much to follow, too many clicks, don't want to get typos, okay, you can copy and paste it out of the chat. All right, but now that we've done that, if I were to run that again and go back to my Lab 5 data files folder, I'll now notice that these are the ones I added before. They're still in here. But now you can see that it loaded in file names with my station in front of it. That way you can keep track of your stations that you're adding and make sure that you glob just the stations that you were interested in. I know that's a lot. Try to keep track of. But go hunt down your stations. Make sure you put your station number in here and put it in here into your glob. Load it into a data frame. Once you've done that, checkbox. You know you've got that data in for that station. Go out, find another station, bring it in there as well. You don't need to delete any files because now we've made it unique by putting the station ID in front of the file name. So the goal for this week until we get to lab next week is wrap your head around this script a little bit. You only have to pay attention to year and station ID. Only two things you really have to look at. I'm not sure, is David still on the line? He said a couple, right? So he said some in the prairies, some on the coasts.
That's right. Yeah, a couple in the prairies, a couple on the West Coast.
Yeah.
And I'll send you a list here. Actually, I'll distribute it through Brightspace. So Toronto has 180 years of data.
Wow.
Almost.
Yes, Julia. I mean, I think David's just going to distribute something that gives you longer range stations over 30 years with some threshold.
Yeah, no, I've been finding here you can't simply subtract the first year and the last because you have stations that started in 1860 and ended in 1906. So they have enough years.
Yeah, but they're way outside the range.
So it's a little more complicated, a couple of if statements to check the first and last.
Yeah. So go hunt down a few stations. David's going to give you a list of stations that have enough years, so you don't have to go wading through ones that have 5 years, 10 years, 3 years. He's going to give you a list of stations that you can select from. Try to select some in the middle of the country, some on the coasts, or at least one coast. Get those loaded in, get them into a data frame, look at the data, okay? You're going to want to probably clean up your data frames like we've learned in the past. You probably don't need 31 columns, okay? You've probably got a date that you can use, all right? Yeah. I thought this was, what do we don't want daily data, do we, David? We want monthly data.
Yes, actually, yeah.
Okay, we may have to change something. Sorry, I read how to do this, but I may have put the wrong. No, it wasn't that one. Read me. Okay, it says here, time frame 1 for hourly data, 2 for daily, 3 for monthly. All right. So do we list station IDs in that case? Sorry if I missed it. List them in the code? not the way we have it written. So let's just go with a no. Do one station at a time. Okay. All right. So everybody paying attention. This is really important. Okay. We want monthly data, which means if we were looking at our metadata, which everybody should have read, right? Even though you're not coding it, but the metadata on the Google site says time frame equals 3 from monthly data. Madeline, are you asking for this? Oh, I just got it. Okay. All right. Everybody paying attention. Drop what you're doing. Look at my screen. 3, 2, 1. Everybody, right now. Go to your get request block of code where it says time frame :2. You're going to want to change that to time frame :3. 2 goes to a 3. All right. That way we get monthly data instead of daily data. Okay, important. Just for fun, I'm going to clear this massive file out and reload mine for monthly data to test it. So again, everybody listening, time frame time frame :3. Just a one-time change. Just make that change and leave it as is. Yeah, there we go. That's better. So 1 file per month per year. Much better. And there it is. All right. Questions? I know that was a lot. That didn't. That didn't help. Huh. Time frame 3, that made it go to every year. Why? That's puzzling. You guys may need to keep it at a 2. Huh. That's what you get from metadata, hey? Time frame equals 3 from monthly data. Two for daily, that's what we were getting. Is not used and can be any arbitrary value. Okay. Strange.
It's not giving you monthlies?
Well, when I changed the 2 to a 3, it's now giving me every year in that was ever recorded. Or up to 2008.
In one file?
Very peculiar. No, all the files.
Okay.
But like it's done this. It's done them only for the files have only done it through the, but everyone's identical. Everyone has downloaded everything. So the parameters haven't changed. Good times, hey.
Found some of the Government of Canada sites not always tended.
Yeah. So you guys may need to leave that just as a 2 because 2 works, 3 is.
I mean, it's easy enough to calculate the monthlies.
Yeah, exactly. I just don't know why changing it from a 2 to a 3 would have made any difference whatsoever.
Let's see here.
Okay, questions? We're kind of at time. I know we've kind of derailed a little bit at the end here, but the examples that I did do work. Okay. Thanks, Julian. Yeah, maybe we leave it at a 2. That's so funny. Their own metadata doesn't work. All right, everyone. Anybody watching the video? Anybody still there? Put the time frame back to a 2. We're going to end up with daily data. For whatever reason, the metadata on the government site has misled us. So we're going to get daily data. Okay. So bizarre. Well, there we go. All right. Questions on that crazy bit of scripting? Hopefully knowing what to add. Only a couple of variables you're looking for here make sense. Questions? Comments? Deep breaths? No? Very quiet. Everybody's in shock. Hey, Megan.
Everybody's sad about the Falcon rocket not landing the other day. I'm not sure I'd want to be a tourist on the first rocket flights.
Madeline, yes. So you're going to go find your station, change the station ID in this line here, and run that. And then you're going to test that your data frame blob works by changing the station ID here, and you'll have your data frame. Then you're going to add arguments to your read CSV to kind of pare down that 31 columns to, you know, just a few that we want to use. You're welcome. And then you're going to find another station, and you can change the station number and execute this again. Okay, making note of the date range that you've had set.
Can we have data from different stations?
Yes, you can, Ed, and that's why we've changed here the file name. We've added station ID to it. Therefore, when you use your glob, you specify the station number